if you're wondering where the coefficient of the viscosity is graphed into the temperature term there. And then we take the temperature to be 310 Kelvin, that's about physiological temperature in which we think these things are occurring. And where we normally have delta function, we decided to deal with the finite time step, and we took that to be just a 10. Anyways, so the second stochastic process that we're dealing with here is the process of the myosin head releasing from actin and ATP binding, and that process right there. And this is a very kind of a crude approximation, but what we do is we just, Q would represent the maximum of the potential, and Vx would be the potential just along the kind of the less sloped side of the asymmetry, I suppose you would say. And we just compare that to a uniform distribution, uniform probability distribution generating a number between 0 and 1. If the potential, normalized potential is larger than that number, we say that basically the myosin head unbinds and experiences a force. Notice that over here at the steeper side, we just say there's no chance of a bind, and that's in a way to simulate the load dependence, because if you think of the load acting this way, then the myosin head is pulled into the side of the potential, and we don't want it to release in that case. So the more you have towards the less sloped side, the more you would like to unbind, so you can kind of maximize the power of the stroke. Okay, so now we can go ahead and look at a couple of simulations. We recently rebuilt the model, so it's not, we don't have very long simulations to show you. But first of all, we have, this is, pause for a second, this is 6 myosin heads without ATP, so all you're seeing is the thermal noise here, and it's only about 10 seconds long, so here we go. Alright, so you noticed probably there that each of the myosin heads seem to, let's see if I can go back a little bit maybe. Each of the myosin heads seem to kind of oscillate about this position that's about a third of the way between each of the black dots. That's the equilibrium, that's the weld of potential essentially. Also a very valid argument. I mean, we would say that this doesn't matter the second law because there's no directed motion time as you can observe. But it's quite clear that we don't have any myosin heads really jumping into potentials. That's because our thermal noise isn't big enough in this case. So you could argue that they're just trapped in the well and you're not really seeing, you're not really seeing the system obey the second law. So that's one thing we need to work on, is we need to amp up the thermal noise, and we can really get some jumping going on so we can show that. So that's the without ATP, and now we have one with ATP, and this one gets a single jump, I think. You notice the full slide there, and then after that it just plays around.
Remind us how you modeled the ATP?
Yeah, go back. Oops, let me pull the PowerPoint in. So again, what we're saying is, how we model before the ATP.
It's the ATP is non-equilibrium. Introduce make it to be non-equilibrium. How do you introduce that into your system?
Yeah, it's.
I understand the thermal.
Yes, I understand what you're saying. Yeah, it's not, I'm sorry, I should have clarified. It's essentially just an impulsive force that acts to the right, and we pick a number and we let it act for a short time step. Okay. So we've shown the two different simulations, and now we can talk a little bit about what we want to do in the future on this project. First of all, we just like to run simulation for a longer period of time. We want to be able to see, that's some certainty obeying the second law. We want to be able to have long simulations with quantitative data that show doing that motion over time. And then once we've done that, we really like to go ahead and try to add complexity. We can add more myosin heads, and actually in the sarcomere you have kind of a three-dimensional orientation with 3 thick filaments surrounding a single thin filament. So you have myosin heads interacting with the actin kind of in a three-dimensional manner, as you can see in the diagram here. And so that's something that we like to include. And then we add more myosin heads, and hopefully we get to a sufficient number of myosin heads where we feel like we can accurately simulate the sarcomere, one sarcomere. And then what we can do once we have that is we can go ahead and try to reproduce physiological skeletal muscle experiments, see if we can reproduce the data. If we can, great. That means the model is good. Maybe we have something in the model that can add some insight into how the myosin system really works. If it's not, if we don't get a good fit with the data, it'll give us a reason to go back and look at our model, see what maybe wasn't right, and try to make some adjustments. So that's the talk. I'd like to thank, thank you. I'd like to thank Dr. Desjardins, my faculty mentor. He's been really helpful with this project. It's been a good time for the past 2 years, and also the hourly program for funding. So some references, and that's going to be questions. Okay, well,
I have one.
okay, yeah.
I have one. When you were showing the first one was just the thermal noise, and did you want to increase the thermal noise to where you'd actually get a jump? How high are you having to increase that?
You know,
What is the-
to be honest with you,
what is that potential?
I just started running simulations with someone last night.
Alright.
I've observed it jump with the thermal noise, but we're having some issues with the model just in general, like getting it to be able to simulate each time repeatedly, and so I think it wouldn't be much. We could definitely get jump. I mean, there's several ways you could do it. You could increase the thermal noise. You could also lower the potential, the potential barriers.
I didn't know how high you had that.
Yeah, it's set to maybe 1. The thermal noise has, and then the variance is about 2 or something like that. So,
If you would now like to look at kinesin on Actin instead of myosin, what do you need to change in the program?
a lot. I haven't really looked at Kinesin at all. Yeah, the answer is I don't know. I haven't read much about it. I know that there's probably people who are modeling it. There's lots of people who are interested in stuff. One question that's really interesting to me is Actin. It seems like everyone always knows Actin, and it's Kinesin's moving on Actin, Myosin's moving on Actin. Clearly, I mean, Actin's important, and it's important structurally too. But it seems like it has some properties that might be interesting. Like for instance, in our model, I think you increase the probability of jumps if you allow the actin filament to kind of contract and absorb some of the energy, so that the jump could be sustained without having the energy of the lever arm kind of snap the myosin head back and